The main application of eigenvector analysis is dynamical systems. We want to study problems that fit this form. It's entitled dynamical because we are interested in the dynamics of solutions. How does a solution evolve or change after we act on it by maybe once, twice, or some indeterminate amount? So as an example of this, you can model population of interacting species. So let's say we've got some location where we're studying the population of rats and snakes, and we can measure each of them in, let's say, in units of thousands, and we can create a vector xk that stores the population of the amount of each population on some year k. Now, when we have a dynamical system, what we want to do is see how those rat and snake populations evolve. So they would evolve according to some sort of equation that looked like this, a dynamical system. We would find the population after 1 year by applying some sort of matrix. Let's say that the rat population the following year, on year k+1, it grows. It's bigger than it was on the previous year, and it also depends on how many snakes these rats eat or attack. But let's also say that the snake population changes. So the snake population depends on the number of rats around and on the number of snakes that were there previously. You can take this and write this system as rk+1, sk+1. You can store it in a vector, and then this allows us to write our system in matrix notation. And this is what we are talking about when we say we have a dynamical system. We have a linear system where the output or the future state is dependent on some previous state. Now, generally, we like to talk about x0 being the initial state, and then we want to evolve that in time. So the eigenvectors determine the evolution behavior. If we take that matrix A, 1.1, 0.6, 0.9, 1.4, you can diagonalize it. You can do a bit of work. Again, pause the video, do whatever you need. You'll find that the first eigenvalue is 2. The first eigenvector is 2/3 and 1. The second eigenvalue is 1/2. The second eigenvector, -1, 1. It's a 2x2 matrix. There are 2 linearly independent eigenvectors because they come from 2 distinct eigenvalues. I can diagonalize it. The dynamics I will study by converting to eigenvector basis. If I take some initial vector written in standard basis 1/3, 4/3, you can show that if you do this type of calculation, where you put the eigenvectors here into a matrix, you can switch basis and you can figure out the name of this vector in B coordinate, in eigenvector basis. It would end up being 1 and 1/3. We can draw in our eigenvectors. So one of the eigenvectors was -1, 1. The other one was 2/3 and 1. So there's about 2/3 and 1. So there's the first eigenvector. Let's say that's V1. And the second eigenvector was -1 and 1. So there's the second one. Those two are non-zero. Each of them will span some kind of line. I now want to evolve this, but I want to evolve it in the eigenvector basis. So if I want to figure out x1, x1 is kind of like saying take A and apply it to x0, but I want to do it in eigenvector basis. And that's the whole point of all of this. Doing it in eigenvector basis is the same as saying just take your diagonal matrix and apply it to the coordinates of that point. That is the point of all of this stuff. So there would be the first iteration. So the first iteration, x1b, would end up giving me 2 and a 6th. And so now I want to graph it. My initial state in eigenvector coordinates was one bunch of v1 and a third bunches of v2. There's x0. x1 was 2 bunches of v1 and a 6th of v2. So it's kind of down here. So there's x1. So if I'm interested in generalizing this, I would just take the diagonal matrix and apply it many, many times. I'll end up with the eigenvalue to the power of n, the other eigenvalue to the power of n, times my initial coordinates. As I go and I evolve this in time, what I'm going to find is that those points will get closer and closer to the first eigenvector axis. As n goes to infinity, this approaches 0. And that means that xn is approximately just 2 bunches of n times 1, 0. But that's what it is in eigenvector basis. Or in standard basis, I basically have some multiple of the first eigenvector. So all my solutions will approach the first eigenvector. In terms of a picture, if I were to draw a trajectory here, I would go through that point and all my solutions would eventually just get closer to that first eigenvector. We only need the eigenvalues and eigenvectors to study long-term evolution. Classifying the behavior by the size of the eigenvalues. In this situation, we had what was called a saddle. And a saddle occurs when one of your eigenvectors is bigger than 1 in magnitude, but the other one is smaller than 1. In this case, the larger one is the dominant eigenvector, so all the solutions will approach that dominant eigenvector. As you go forward, as you evolve in time, all solutions approach there. And if you kind of go negative in time, you could see that you could imagine that things would start from the smaller eigenvector and approach the bigger one as you evolve in time. If both of your eigenvectors are smaller than 1, what's going to end up happening is that eventually you will have all of your trajectories approach 0. And so you'll end up getting a picture that looks kind of like this. You'll end up with something that's called the origin here would be an attractor, because all solutions go to 0 as you evolve them forward. If one of them is a dominant eigenvector, eventually solutions will come into the origin along a dominant eigenvector. They will, running the story in reverse, they'll come from the weaker eigenvector in toward the dominant eigenvector. So the origin is an attractor, and if the situation is reversed, then the origin is what we call a repeller. It gets rid, or it repels, all of the trajectories. And again, it always ends up on a dominant eigenvector. And that's it. When you've got real eigenvectors and real eigenvalues, this is how the behavior goes.